Okay. All right, so this is the very last part of equilibrium HL, which is that topic 17. And we had already, the rest of this stuff we had already covered, how to do the ICE charts for calculating, your initial concentration, change of concentration, equilibrium concentration in the different situations. So the very last part, though, we needed to go back and finish topic 15 before we could do this, because it relates delta G, which is the Gibbs free energy, it relates it to equilibrium. And so when you watch the pre-recorded videos, you should have seen this, so I'm not going to go into a lot of detail. You can kind of go back and watch those if you want to. But essentially, and in the videos, there's actually two different diagrams, so make sure that you have kind of both of them labeled on here so that you know, because one is for a spontaneous reaction and one is for a non-spontaneous reaction, and they look slightly different. Okay, the certain areas are the same, but the shape of them is a little bit different, and so you need to know how to be able to tell which is spontaneous and which is not spontaneous. But basically, like it says here, when you get to the minimum value of Gibbs free energy, that's when you're at equilibrium, and so that's right here at the very bottom of this line on the graph. Okay. And so you can see they have labeled here, like this would be the Gibbs free energy of the reactants and the products. So when I subtract them, I would get this diagram, I would have a negative delta G, which means it's spontaneous. The other graph they're going to show you in the video, it's going to have a positive delta G because the products will be higher than the reactants, and so that's your non-spontaneous. Okay, but whether it's spontaneous or non-spontaneous, the bottom of the graph is always where the reaction's at equilibrium. Okay, and it also corresponds to maximum entropy. So you have minimum Gibbs free energy, so the lowest Gibbs free energy value, the highest amount of entropy, that's when you're at equilibrium. Okay. There's a equation that you use to perform calculations using this. Okay. It's in your data booklet, so you don't need to necessarily memorize this equation. You just need to know where to find it so you can use it. It's in the very first section where it has several different equations. And so you use the standard change in Gibbs free energy. You use the universal gas constant, which is always going to be this number. You have your temperature. Temperature has to be in Kelvin. And then you have the natural log of K. And remember, K is your equilibrium constant. Okay. And so you can rearrange this to solve for the equilibrium constant. So if you're asked to solve for delta G, then you would straight up just use the equation like this, plug the numbers into the calculator, and go. They might, on the other hand, ask you to solve for the equilibrium constant. If they ask you to solve for the equilibrium constant, you have to rearrange it so it looks like this. So you will be using the natural log or the E button, not the scientific notation one though. Let me go to my, where's my calculator? Is there a calculator on here? I thought there was a calculator on here. I guess there's not. But in your calculator, you'll need to use the button that looks like this lowercase e, not like the one we use for scientific notation, okay? And so you do e raised to the negative delta G divided by R times T. A couple of things, your delta G, usually you have to convert it, because if you remember, delta G is usually got kilojoules per mole, and we have to convert it to joules because, again, if we look at the gas constant here, the gas constant has joules in it. Okay, so a lot of times you'll have to divide by 1,000 to go from the kilojoules to the joules. So keep that in mind in the problem. And they do this example in the video that's already on Canvas, and you actually do have to do that. They actually do divide, I'm sorry, not divide, they multiply, because you're given the value in kilojoules and you need to convert it to joules, so that means multiplying, not dividing. Okay. So just be careful that you might have to do that conversion between joules and kilojoules. And then if they don't give you the temperature in Kelvin, if they give you Celsius, you remember you'll have to convert that to Kelvin before you can plug it in as well. So in the example video that's on Canvas, they go through this example. So I'm not going to go through like the whole thing. On this one, you're actually calculating the K value. So you're using this equation. If, on the other hand, you were asked to calculate delta G, because maybe they wanted to ask you, is the reaction spontaneous or non-spontaneous? And the only way to answer that is to calculate delta G and see if it's negative or positive. Then that's where you would use this form of the equation here, okay? And then the very last part that's on your video notes already on Canvas is this table that it kind of shows the relationship between these two things, okay? So here's delta G values, kilojoules per mole, and here are equilibrium constant values. And so what it says, the trend that we can see is that as delta G becomes more negative, because if you look here, it's positive 141, positive 79.9, and then now it's negative, and now it's a larger negative number. So as delta G becomes more negative, meaning more spontaneous, the value for the equilibrium constant increases, okay? Here, this is really small because it's to the negative 25th power. It goes a little bit bigger because it's only to the negative 14. Now they're positive exponents, so it's getting larger and larger. So as delta G becomes more negative or more spontaneous, your equilibrium constant value increases, okay? And then, it says here, conversely, the opposite would be true, okay? So as you get more positive, less spontaneous for delta G, your equilibrium constant decreases. And so that's the general trend, and it's just illustrated with these reactions that we're showing here on this table. And then kind of the summary here, it says for a reaction with a larger value for delta G, the equilibrium lies to the right. So larger negative value for delta G, equilibrium lies to the right, and the reaction almost goes to completion, okay? As like this last reaction with zinc and the copper ions, okay? The equilibrium mixture will contain mostly products, okay? For the other one, it's the opposite. If you have a larger positive value for delta G, equilibrium lies to the left. Equilibrium mixture will contain mostly reactants. It says as in the decomposition of SO3, which is this very first one. It's got the highest positive value, and so it would have mostly reactants because it's not spontaneous, okay? The other one, this one would have mostly products because it is spontaneous because it's got this negative value. So that's just kind of showing you how they are all related to each other. And that's pretty much it. That there's not a lot of other information for today. So we just really needed to finish that last part today.